Okay, guys, in this second video on oscillations, we will finish with the material related to topic, I believe, 10 on oscillations, and we will start with energy in SHM, which means simple harmonic motion. Okay, so let's use the pendulum example. Okay, so let's say that the pendulum starts from the top position, so from a maximum displacement to the left. Okay, and let's call this point A, let's call this point B, and then if it starts from up there, it will move to the right through the position of equilibrium all the way to the left to position, let's call it C, and then it will move back to position, let's call it D now, which is the same as position B, but the direction of motion of the pendulum is in the opposite direction, and it will go back to A eventually. Okay, so if this height is h, which is a problem that shows up every now and then, we can actually find Vmax, and Vmax is the velocity that the pendulum will have at positions B and D, again with the only difference that the sign will be opposite because the motion is going to be in opposite directions at points B and D. Okay, so we can just use the principle of conservation of energy. So immediately we see that the potential energy at A is mgh plus 0 kinetic energy because it starts its motion up there. And this should be equal to the potential energy at B, which is 0, plus 1/2 mv squared. And we're going to name this V max because that's the maximum velocity the oscillator can have. So immediately we see that V max is the square root of 2 times g times the initial height h. Okay, so this is a problem that people give to students sometimes in the A-level test. And don't forget that also in SHM, Vmax is equal to the angular frequency times the amplitude. Okay, so you can actually combine these two to find the angular frequency or the amplitude. It depends on the type of problem they will give you. All right, now now for the general case, when we deal, let me use a clean page. So I'm sorry, for the general case, if we plot energy with respect to displacement in simple harmonic motion, and it can be and let me make better letters. I'm sorry. So this is displacement, and this graph can be used for both the pendulum and the spring case, okay, or any oscillation for that matter. So the maximum energy is actually 1/2 mv max squared because energy is conserved, right? So if we plot the kinetic energy, and if we go back to this scheme, remember points A, B, C, and D that determine the motion of the object. So if we plot with red the kinetic energy, if this is minus A and this is A, so this is point minus A is point A in the scheme we used earlier, right? So this is point A, and this is point C, and this is points B and D. Okay, so at point A, the kinetic energy is 0, and the same goes for point C because the oscillator stops. But at points B and D, we will have a maximum kinetic energy, 1/2 V max squared. And it doesn't matter what the sign of the velocity is because if we square it, we get a positive sign. So the kinetic energy increases all the way to 1/2 mv max squared as the oscillator moves, and then drops to 0, right? Now at point A, what's the potential energy? Let's use blue. The potential energy, let me draw, let me make this, okay? So the potential energy is mgh, or 1/2 kx squared in the case of the spring, but in any case, the potential energy is equal to the maximum kinetic energy, okay? So the maximum potential energy is equal to the maximum kinetic energy. So at point A, we have the maximum potential energy. Then the oscillator goes to point B, so it has no potential energy there. And then again, it goes to 1/2 mv max squared, okay? So as the oscillator moves from point A to point C, the potential energy increases like that. And notice that if we add, let me use a different color. Let's use orange. I don't know why I like orange so much, but anyway, if we add them up, we see that this is the total energy, okay? The total energy is equal to the potential energy plus the kinetic energy. And at any point in this motion, like here, for example, if we add these two guys, we get this. If we add this and that, we also get this. If we add this and that, we get this. And if we add this and that, which is the potential energy and the kinetic energy, of course, we get a total energy that is constant. Okay, so I'm gonna write it down here that the total energy in simple harmonic motion is constant and equal to 1/2 mv max squared. And this is also equal to 1/2 m omega squared times the displacement squared. Why? Because Vmax, don't forget that Vmax is omega times A. That's it. So these are some nice thing to have in, like a piece of information to have in the back of your mind. So pretty much what happens here is that all potential energy initially converts into kinetic energy, and then all kinetic energy converts back to potential energy, and so on and so forth, okay? And this is, of course, the ideal case in which we have no friction, but in real life, we always have friction, okay? And to prove mathematically that the total energy is constant, I'm going to do some optional math here, okay? So I'm going to type it as optional math, okay? So E total is, as we saw, kinetic energy plus potential energy. But for the case, I'm going to use the spring case, okay? In the spring case, the kinetic energy is 1/2 mv squared, and the potential energy is 1/2 kx squared. That's from your AS level physics, okay? But as we saw, the velocity is given by omega times A times sine omega t, and I need to square all this, okay? And x, the displacement, is given by k times A squared times cos omega squared at, right? Because the velocity is the first derivative of the displacement. So if the displacement is cos omega t, the velocity is going to be minus sine omega t, and then squared is going to use sine squared omega t, okay? And then if we use the fact that k is m omega squared, we find that we have 1/2 m omega squared a squared times sine squared omega t plus cosine squared omega t, which adds to 1, and we get 1/2 m omega squared a squared, okay? And is there anything else I want to talk about? Oh, k is m omega squared for the spring, because recall that omega is the square root of k over m. So if we take the square of omega, we get k over m, and so on and so forth, okay? So you can see that even mathematically, we get that the total energy is constant, and something similar can be proven for the pendulum, which is exactly the same case, okay? Now, the next thing I want to talk about is the concept of a resonance, okay? A resonance is caused by an external driving periodic force. Let me write it down and I'm going to try to explain. If an external driving periodic force drives, as we say, the oscillator, meaning that it puts it in motion, a resonance phenomena can be observed. So what I mean is that if we are dealing with a spring, let's say it's attached to a wall, okay, and this is an object of mass m, and the driving force will be, for example, a person pulling this spring back and forth, okay? So this is the driver. Like maybe I pull it in the beginning and then I keep pushing it. Once it reaches a maximum amplitude, I keep pushing the spring back and forth. Another example is the swing. Like if someone is swinging and you keep pushing them, the moment they reach their maximum amplitude, then you're gonna make them move at an even higher amplitude, right? At an even higher height, because you provide energy all the time. So this is what the driving force is. Now, if it happens, so the angular frequency of the driving force is equal to omega naught, where omega naught is what is called the natural frequency of the oscillator. So omega naught is the natural frequency of the oscillator, which is omega naught, for example, is the square root of k over m for a spring, and omega naught is the square root of g over the length of a pendulum, okay? So that's the natural frequency of these two objects, okay? So if the driving frequency is equal to the natural frequency of the oscillator, then the amplitude of the motion becomes very large. And we get a resonance. Okay, this is what it's called. So to give you an idea, if we plot the amplitude of an oscillator with respect to the angular frequency, and if somewhere here is omega naught, is the natural frequency of this said oscillator, then for frequencies below the natural frequency, the amplitude will increase steadily until we approach omega naught, in which case the amplitude theoretically gets infinite. It doesn't in practical applications, but theoretically it can get infinite. And the same goes on the other side. If the angular frequency of the driving force is very different from the natural frequency, then the amplitude is small, but it increases as we approach. Sorry about this bump, it shouldn't be there. It increases, oops, and at omega naught it becomes kind of infinite. Okay, so I'm gonna write it here, almost infinite. Okay, now this is dangerous for practical applications, like in buildings, in areas of the world where they get earthquakes. The building has a natural frequency of oscillation, believe it or not, because it consists of a structure that involves concrete, actually reinforced concrete. So it has steel in it and concrete and all these nice things. Or there are other buildings like skyscrapers, they are made out of steel, I believe. So they can oscillate. Okay, it takes a particular frequency for them to oscillate, but let's say you have an earthquake that happens to have the same frequency as the natural frequency of the building. Then the amplitude of oscillation, the building is going to start oscillating at maximum amplitude, and there is a danger that it will fall. Okay, so I'm going to write this down. This is dangerous. For constructions such as buildings, bridges, etc., as they might collapse. Okay, and there is this famous example in America of a bridge that resonated with the wind back in the day. I don't remember in which US state it was, but there is a live video showing the oscillations of the bridge until it collapses, which is kind of scary. Okay, one more thing. This is optional, and this is not something you were taught. So I'm going to write it here as out of scope, but I'm going to mention it anyway, is that if the force, the driving force, is equal to some force F naught times cos omega t, where omega is the angular frequency of the driving force, and with omega naught, the natural frequency, then the amplitude is given by this formula. F naught, the amplitude of the driving force, over the square root of m, the mass of the object, times omega squared, the frequency of the driving force, minus the natural frequency squared, and the whole thing squared. Okay? So this is the formula. And this is why we see this behavior here. Because notice that if omega is omega naught, the denominator is 0, right? So F naught over 0, which is infinite, right? So this is why we get resonances. Even mathematically, you can kind of see that. And okay, next in line is the concept of damping. Not damping your boyfriend or girlfriend, damping as in reducing the oscillation's amplitude. So if a resistive force acts on the oscillator in the opposite direction, than the velocity, damping occurs. So the damping force, let me fix that. So the damping force is proportional to minus v. Okay, so it's in the opposite direction than the velocity. And to demonstrate, imagine that we have a cup of water. Actually, let's make this blue. Okay, so maybe we have some fluid, and maybe we have a spring, and maybe at the end of that spring there is a mass. Okay, that maybe it moves down. Okay, so that's the velocity down. So the oscillator tries to move downwards, but the fluid is gonna exert a damping force in the opposite direction, right? Because it's gonna push it up. Also, there will be some buoyancy here, okay? But the damping will be a force that is upward and it pushes the oscillator in the opposite direction. Therefore, it slows it down and it reduces the amplitude, okay? So depending, let me use a clean page. So depending on the strength, I'm going to explain, on the strength of the damping, we have 3 types of oscillations. It would have been better to write damping oscillations, but anyway, you get the point. So the first one is underdamped. So in this kind of motion, the oscillation dies off. Dies off gradually. In an oscillatory fashion. The period of this oscillation is close to the natural one. And there is an exponential there is an exponential, envelope around the oscillation, and I'm gonna use a plot to demonstrate this. Let me use a clean page maybe. So if we plot x with respect to time for this type of oscillation, and this is the maximum amplitude, a and minus a, so I'm gonna use blue to plot the actual oscillation. So the actual oscillation looks like this. It's the, before damping. If we introduce damping, let's use green. If we introduce damping, we will observe something that looks like this, maybe. Okay, so the frequency will be about the same, as you can see. Okay, but the amplitude is gonna gradually reduce, etc. Okay, and the exponential envelope is this. Okay, if we connect the tops of these amplitudes, we will see that gradually the amplitude gets smaller in an exponential fashion. So if I could use a whole plot, the amplitude will decay like this. Okay, something like this, but the oscillation will look like this. Okay, and actually it's gonna decay from this side as well, and the underdamped oscillation will look like this. Okay, so it will still oscillate, but in every period the amplitude will get smaller and smaller and smaller. Okay, so this is the underdamped. Oops, did I say? Yes, it's the underdamped. Yes, it's correct. So this is the underdamped oscillation. Okay, so the driving force is kind of small, so it still allows for some oscillation, but it still reduces the amplitude of oscillation. Okay, the second type is critical damping, which is a desirable situation, especially in cars. I'm gonna try to explain. So the second one is critical damping. So this is desirable, and oscillation dies off fast and exponentially. So if I were to plot this situation, okay, if this is the displacement again with respect to time, and actually let me use this is maximum amplitude. Okay, so if this is your initial oscillation, something like this, for example, is your initial oscillation, critical damping will make it die off really fast, so something like this. Okay, so it dies off really, really, really fast, and you get an exponential decay. I'm talking about this part. From here and to the right, we get an exponential decay, a fast decay of this oscillation. Okay, and this is desirable in cars, for example, where if you fall into a bump in the road, you don't want your car to keep oscillating. You want it to oscillate a little bit to absorb the bumping, I guess, but then you want it to go back to equilibrium pretty fast. Okay, and the third type, let me use black. Third type is overdamping. In overdamping, oscillation dies off slowly. Dies off slowly, but exponentially. Okay, so again, if we plot this, and by now I hope you got the idea. This is the amplitude, and this is the original motion before damping. Okay, so the original motion looks like this. Okay, then overdamping will look like this. It will start, and then it will start decaying, but very slowly. Okay, so it will start oscillating up to this point, and then to the right of that point, we get an exponential decay, but very, 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 very slowly, compared to the exponential decay we get here, which is fast and it goes to zero. Whereas in overdamping, it doesn't really go. It goes to zero, but it takes a long time. So it's not an ideal situation in applications. And when I say applications, I mean engineering applications, so civil engineering, mechanical engineering, that kind of thing, okay? And last but not least is combining these two things. We talked about damping and we talked about resonance. So what happens if we get both at the same time? So let's see. Damping and resonance. So this occurs when we combine a driving force and a damping force. And this is what is most realistic in applications. So we still get the maximum amplitude if the driving force angular frequency is equal to the natural frequency, but damping moves the maximum to lower frequencies. So let me write it down and I'm going to explain. So we get a maximum amplitude if the angular frequency of the driving force is equal to the natural frequency, but damping moves the maximum to lower frequencies. And let me turn a clean page. So if we plot the amplitude like we did before with respect to omega, and if this is omega naught, which is the natural frequency of the object, then again, remember when we saw that with no damping, we get these infinite curves. So that's no damping. Let me use green now. If we have light damping, we will get something that looks like this. It will increase by a lot. And at omega naught, we will get the maximum. So this is light. Oops. This is light damping. Now, if the damping force is larger, we get some sort of heavier damping. Let's find another color. Let's use this pink. So if we have a heavier damping, we will get this graph, okay? Notice that it's maximum shifted to a lower angular frequency, okay? So this is heavier damping. And if we use an even stronger damping, we will get something that looks like this. So we still get a maximum, again, at a lower angular frequency, okay? So this is heavy damping. Okay, so notice how, let's use yet another color. Let's use, which one? Let's use purple. So notice how the maximum of these curves moves to lower angular frequencies, okay? So this is what we mean that damping, the heavier the damping, the lower the frequency, the maximum amplitude will be observed, okay? If this doesn't make sense, guys, please ask for questions in the comments, okay? Now, the underlying math, in case you're curious, which is again out of scope, you don't need to know things like this at the A level, but those of you who are going to study engineering or applied math or that kind of thing, you're going to learn about this. So underlying math, which is optional, tells you that A, the amplitude, is equal to F naught, and F naught is like before, is the amplitude of driving force, okay? And in the denominator, we will have m times omega squared, which is the frequency. Omega is the frequency of the driving force. Omega naught is the natural frequency squared. This is exactly the same as the one I showed you before for, where was it? Sorry, here for resonances, okay? But because of damping, we get an extra term in the denominator called b squared omega squared. And this b is what determines how strong damping is, okay? So that's damping, and omega is the frequency of the driving force. So you immediately see how if b is 0, we get the same result as we had before. And then as we increase b, this amplitude moves to the left pretty much, okay, to lower frequencies. Okay, and one last thing before I close this video is the concept of materials and damping. So materials and damping. Remember when I said about buildings oscillating due to an earthquake or maybe air or some external force? Then because of this, it is best to use materials that can withstand a lot of plastic deformation in construction, okay? So in buildings, cars, machines, and so on and so forth. So it is best to use materials that can withstand a lot of plastic deformation so that they can absorb the energy of the driving oscillation. The driving oscillation will be the earthquake, for example, in the case of a building, okay? The driving oscillation, the energy of the driving oscillation, sorry, without breaking. So this is why we use, for example, reinforced concrete. Reinforced concrete is concrete that that has steel in it, okay? So you use some steel and then you pour in the concrete, and that makes the whole thing more plastic, if you will. If you had only concrete, what I'm trying to say is that concrete is brittle, so any earthquake would kind of shatter that and make the building collapse pretty much. So by introducing reinforced concrete, so by introducing steel into concrete, you make the thing withstand larger periods of oscillation and larger amplitudes of oscillation without breaking. So this is why buildings don't collapse, especially in countries such as mine, actually. I come from Cyprus and we have some earthquakes, not very, very strong, but we do. But there are earthquakes in Japan, notoriously, and California, San Francisco. So they try to make buildings that can absorb these pressures from earthquakes. Otherwise, all their buildings will collapse. Anyway, this is it. We are done with oscillations as well. In the next video, we will talk about gravity and space and interesting stuff like that. Guys, let me know in the comments what you think about these videos. Like and subscribe and share with people that might find use for these videos.